Hi. We have seen that the eigenvalues of an n by n matrix are the roots of a certain polynomial of degree n. As you probably already know, every root of a polynomial has a multiplicity. For example, consider the polynomial f shown here. This is a polynomial of degree 6, and it turns out that it has the factorization shown here, which is not easy to find, by the way, but you can easily check it. The factorization reveals that f has the roots 5, 1 and minus 4, with the multiplicities as listed in this table. The sum of the three multiplicities is equal to 6, which of course is equal to the degree of the polynomial f. Back to our context of eigenvalues. There are two types of multiplicity of an eigenvalue which play a role in linear algebra. The first is the one I just discussed by means of an example, and the second is essentially different. Here are the definitions. Let lambda I be an eigenvalue of an n by n matrix A. Then the algebraic multiplicity of lambda I is equal to the number of times the factor lambda minus lambda I appears in the characteristic polynomial of A. Secondly, the geometric multiplicity of lambda I is equal to the dimension of the eigenspace E lambda I. Note that AM of lambda I is at least equal to 1, because lambda I is a root, and it is at most equal to n, because n is the degree of the polynomial. Also note that Gm of lambda I is at least equal to 1, because lambda I is an eigenvalue, and it is at most equal to n, because the dimension of a linear subspace of Rn is at most equal to n. Let's have a look at some examples. Firstly, consider the matrix A shown here. Its characteristic polynomial factorizes into lambda minus 1 times lambda minus 2, which follows from the calculation inserted here. Hence, the eigenvalues of A are equal to 1 and 2. Let's find the corresponding four multiplicities and list them in this table. Both factors in the factorization of the polynomial occur just once, so both eigenvalues have an algebraic multiplicity equal to 1. What about the geometric multiplicities? The matrix A minus I has rank 1, so its null space has dimension 1. The same holds for the matrix A minus 2 times I, so both these null spaces have dimension 1. These null spaces are the eigenspaces of A, hence the two geometric multiplicities are equal to 1 as well. To compare, let's do the same computations for the matrix shown here. Its characteristic polynomial is equal to lambda minus 5 squared, so A has one eigenvalue 5 with algebraic multiplicity equal to 2. The matrix A minus 5 times I has rank 1, so the null space of this matrix has dimension 1, hence geometric multiplicity of the eigenvalue is equal to 1. In the two examples, we have come across the multiplicity combinations shown here. Can you think of an example of a 2 by 2 matrix which has an eigenvalue with geometric multiplicity equal to 2? The identity matrix is such an example. Indeed, since A times x is equal to 1 times x for all x in R2, we have an eigenspace of dimension 2 here. Note that for this example the algebraic multiplicity of the eigenvalue is equal to 2 as well. It turns out that the table shown here lists in fact all possible combinations of the two multiplicities for a 2 by 2 matrix. Similarly, here's a table with all possibilities for a 3 by 3 matrix. In general, we have the following theorem. Let A be an n by n matrix, then for each eigenvalue of A, its geometric multiplicity is smaller than or equal to its algebraic multiplicity. This is an important inequality in linear algebra. Note that we can add these two trivial inequalities that I referred to earlier in this video. Finally, let's have a look at these three examples, A1, A2 and A3. They all have the same characteristic polynomial, 5 minus lambda to the power 3. Hence, they all have one eigenvalue 5 with algebraic multiplicity equal to 3. What about the geometric multiplicity? Well, if we subtract 5 from the diagonal entries, we end up with a matrix of rank 0, 1 and 2 respectively. Hence, the GM of the eigenvalue 5 is equal to 3, 2 and 1 respectively. So, now you know in principle how to calculate the multiplicities of an eigenvalue. The full list of multiplicities of the eigenvalues of a matrix provides important information about that matrix, which often plays a significant role in applications.